Structuring systems, an application of basic structural modeling. This is the fifth part of this series. We'll have one more part, part 6, which will be a summary and conclusions. And in this part, the fifth part, we will finish up the final steps in this particular structuring activity. So again, my website can be found by following this link. It's my Twitter feed. The website has a lot of background information plus the existing original charts that you can download and use to follow through the video. So I'm going to go through the introduction to fundamental concepts and the general process steps and the specific process steps rather quickly. We've gone through these before in the other parts, and then we'll focus on the last parts of the last two parts of the main process steps in this video. And of course, the particular activity here in structuring systems, we start with 19 cities in an unknown and unordered state, and our objective is to order these using a combination of inference techniques and empirical data that's collected. And the particular way that we do this, we want to minimize the amount of empirical data that's collected so we can minimize cost. So we start with 5 cities, and then we collect 5 data points for each one of those cities, and we analyze those and move forward and do that again. Select 5 cities at random, select 5 points associated with each of those cities, order those, do the inference. But then in the third round, where we deal with the cities, we are actually now going to do one city at a time and start exploring the inference potential and how we can maximize the use of inference and reduce the amount of effort necessary to collect the empirical data. So the fundamental concepts here, basically there's 3 types of truth. There's formal truth, factual truth, and value truth. And we've created an approach that uses the same computational system. Earlier in this work, we analyzed open source tools, math tools. We selected the SAGE math tool from the University of Washington. That information is on the website. The authors have developed an abstract relation type, which will be used to integrate the truth operations. And the abstract relation type has a marking space which supports the encoding and evaluation of formal and factual truth, and a value space which supports the operations on value truth. And of course, these all work on a system structure, and of course the system has components. So the types of truth here, we have formal truth, which is essentially formal logic, factual truth, which depends on the state of the real world, and value truth, which is dependent upon the context and the set of values that are being applied in any specific instance. There's a little more detail on types of truth. What we're doing here is we're actually, if you look at known by experience, factual truth is known by experience. And this is, we want to leverage our factual data using formal methods and use those in a way that will help us achieve the types of values that we're looking for. So this, and of course the other idea about certainty that's associated with these types of truth is, of course, that formal truth is certain, factual truth is not certain, of course, and value truth is not certain. So there's uncertainties introduced here, but it's also managed. It's kind of a very general idea of abstract relation type structure. It has 3 spaces: a marking space, outcome space, and a value space. And each of these spaces can have 1 or more matrices. Here we show a value space with multiple matrices, but a marking space could have multiple matrices, and so could the outcome space. Just a general type of high-level conceptual architectural approach or understanding of what an abstract relation type looks like. And the abstract relation type is also designed to integrate and support the communication of three types of information. That's prose descriptions, graphic representation, and mathematics and computer representation. These particular components then are applied to a system model. The system model itself essentially is represented in any one of these three types, and we talk about a model exchange isomorphism, which means you can have a graphic description and change that to a mathematics description without any loss of information, or a mathematics description and change it into a prose description without any loss of information about the model. So we really are going to use the abstract relation type to support the model exchange isomorphism concepts and methods. And of course, the mapping, context for complexity, and system structure and its components. Really, the idea of a system concept, we usually use systems concepts in one or two modes, either a design mode or a discovery mode. And most graphic representations within the systems area are in the design mode, but we're going to be using the graphics, and our activities are going to be in the discovery mode down here, where we know the objects, we know the cities, and we're discovering the relationships between them. So system structure and the components. We define a system as a relationship mapped over a set of objects. So we know the cities, the objects, we know the general relationship, which is north of. We have to discover the specific relationship between each city pair. And these are the general process steps that we're going to go through. In the previous parts of this video series, we've gone through steps 1 through 7, and we're going to finish up with steps 8 and 9. So we'll just kind of quickly run through these first 7 steps. Of course, this is our beginning configuration where we initialize the step when we have 19 cities, and the yellow zeros mean that's unknown. We really don't know if city 10 is north of city 1. Well, we don't know. Is city 4 north of city 7? Well, we don't know. There's a 0 there. And you can see that there's zeros on the diagonal, but there's a red background. And what this says is city 1 north of city 1. We don't need to collect information to determine that. Well, logically, we will not allow a city to be north of itself. So we put a red 0 there. We know that city 1 is not north of city 1. Makes no sense. City 10, is city 10 north of city 10? Well, no, we won't allow that. So then we collect the empirical data. And the empirical data, the true is marked with a green 1, and 0 is false is marked with a red 0. So this says, is city 2 north of city 1? Well, yes, it is. So then we can infer from that that city 1 is not north of city 2. And then we have these pairs of information selected at random. You can see kind of a scatter plot here. And then we go through and start ordering this. This ordering process that we're going through here is part of our conceptual design study, and the ordering process and ordering code is one of the outputs from the specific design work that we'll do later on. So we'll start swapping these rows and columns and moving the green ones into the lower triangular. Move them from the upper triangular to the lower triangular. Just kind of walk through here. See, we've got our green ones. We're going to be moving them down into the lower triangular. And then also we can see that the first row is going to have a city that's going to be all zeros. There will be no ones in this top row because nothing is going to be north of the city in the top row. So you can see that green one here has been moved down, and keep moving the green ones down, and we're really finishing and stabilizing this area up here and moving these green ones we have left, moving them down into the lower triangular. You can see now that this whole area up here has been cleared of green ones. We have some more green ones down here to clear. And we'll just keep doing that until now we've moved all of the green ones into the lower triangular. We have all the red zeros in the upper triangular. So now what we need to do, of course, is perform the inference operation. And these blue ones, now we've used the empirical data we have and we've inferred that these blue ones are true. That now that these specific items here are true. The ones with the blue ones, and of course the green ones are true from empirical, the blue ones are true from inference. And this is the inference process. It's detailed in Warfield's work. These are the matrices. This is the structure matrix here in D. Here's the identity matrix. They're combined and then they're multiplied until they don't change anymore. That becomes a reachability matrix for that particular section. And then here's our decimal to Boolean mapping that we're doing here. So we've now run through steps 1 through 4 in a general process check, and we will now review again steps 5 through 7. So what we're going to do now is collect more empirical data, 5 more cities at random. And you can see that the random disposition of the green ones in this particular new matrix here. We're going to do the same thing. We're going to take the green ones from the upper triangular, move them into the lower. Just move them as we go through. So you can see this upper triangular now, we're no green ones up here, and we're going to take these and move them into the lower. We're swapping these rows and columns to change the configuration of the system. We still have the same system, we have the same objects, we have the same relationship. We're just changing the configuration or the ordering of these objects, and that's the purpose of this particular exercise, is to order these cities, going from an unknown ordering to a known ordering, but we're minimizing the amount of empirical information needed to do that. So we'll get these green ones in the upper, get them into the lower. So we got one more down here. Look at that. So once again, we've gotten all the green ones into lower triangular. So now we'll do the inference again. Here's a general process of inference. But actually this is the ordering process. So in the general ordering process, we're going to look at what the final matrix is going to look like. And then we will create a value matrix, and then we will combine those in a way that we can use a row. We can sum each row in the outcome matrix and use that as a marker to tell us which, or help us select which row should be moved. So this is kind of what it looks like. This is the final. When we're all done, everything is all ordered. All the ones are in the lower triangular. All the zeros are in the upper. And we take this matrix and we do a cell-by-cell multiplication of this value space, and it gives us this outcome space down here. We sum these, each row in this outcome space, the row sum. Here are the values that we have. You notice that there are no ones in the first row. There's 1 1 in the second row. And so as we move forward, you can see more and more and more larger and larger values in the row sum going. And this is an indicator that we will use or test out in our code to help us select which rows need to be swapped. So once we've ordered those, then we'll do the inference. We have new inference data. It's going to be in this particular group, and these are the inference steps again. So this general process check, we've moved through the first 7 items that we've gone through in the other video portions of this series. Now we will move on to the next section, where we'll start looking at selecting the highest inference potential for each row or column swap. So here it says we're going to swap columns 11 and 17. So let's go back and see what we had. Right here we had 11 was at the top, it's all zeros. We have 17, it's all zeros. We know that one of these has to be north of the other, but we're really not sure which one it is. So we'll collect empirical data on that. So we'll go collect empirical data on row 17 and row 11. So this says, is row 17 north of row 11? Yes, we went and collected the empirical data. We found out that row 17 was north of city 11. Well, it's city 17 north of city 11. And it was, so we swapped that row and column. And then we swapped these next row and column, because once we did that, we had a 1 up here, 11 and a 2. So we'll need to swap those. And now we have a 2 and a 1. So we'll need to swap that. Now everything's ordered again. So we'll need to select the next set of cities to collect data on. So we have a 1, here's a 0 and a 1, and it's going to have 1, 1 in that row, and here's 13 and a 1, and they're in different columns. So we'll find out the relationship between city 3 and city 13 by collecting empirical data. And so here we found that city 13 is in city 3. So is city 3 north of us? Is city 13 north of city 3? And the answer is yes. So we then swap those rows and columns, and then we will need to, because of that swap, we have a 2 and a 3. So city 3 and city 2, they need to be swapped, so we'll swap those rows and columns. And we have city 2 and city 1, again we need to swap those. And now here we have city 2 and city 1. And see, here we had city 2 and city 1. And now we're going to have city 2 and city 1. Here we go. And there's city 19 and city 3. So we swap those, and now we have city 7 and city 3. And keep swapping these rows and columns as we go through and collecting information as necessary. So we'll have 16 transforms here, which we based on collecting 3 empirical data sets. So we've really leveraged the ordering of the system. We only needed to take 3 empirical sets of data, and we were able to then order the rest of these. Of course, once these are ordered, now we'll do a inference, and this inference now gives us all these new blue data points that say yes, these are actually north of them, north of these other cities. So all the blues that we added in now are inferred. So we need to collect more data and go through one at a time. Because you notice we started at the top, or the top left-hand corner in the upper triangular, and we're moving down through toward the lower right-hand corner of the matrix in addressing and ordering these cities. So column 1 and 15 we changed, then column 6 and 1, then column 5 and 8, and then columns 2 and 4, and 4 and 5, and then 16 and 18, 18 and 19, and then we're done. So we took the this process and looked at these one at a time in these last 2 parts of the process, which will look promising and something that we may want to put into our code, in our final code. And then we've gone through and looked at the cities in relationship, and of course the process summaries identify the cities in relationship, start with random selection of cities, and then we execute the ordering and inference processes, which of course is what we're designing. Right now we're just in the conceptual design phase. pick individual data points. That's what we did in these last set of cities, and then execute the ordering and inference process for the individual cities. The conclusions of the process test was successful. The known order was reproduced. Semi-automated steps need to be automated. That's a job for the next series of programming steps. We need tighter code and process integration, and the graphics appear to be useful, and so we're going to really move on to detailed code design. But we really have one more series of slides to do, and one more video which will encapsulate and talk about everything we did in this first video series.